If you recall, when we looked at what the syllabus actually said about differential equations, there were basically three types that they might ask. One was where the derivative was equal to a function of x times a function of y, and that's what we looked at in detail yesterday with separation of variables. The other was the derivative equals some function of x, which really is what we've been doing all along anyway. Well, that brings us to the third case. What happens if we've got a derivative equals some function of y? So of that form, well, again, you can just simply separate. It's really no different to yesterday. It's just that the function of x is 1. So we can treat it exactly the same way, and we end up with the integral of the x is the integral of the y over whatever that function is. It is still a first order linear differential equation because I could rewrite it, and as I say, that's where function x is equal to 0 if I wrote it that way. Here's a differential equation which you may recognise. It actually is something we have seen. We've been giving an initial condition there of, when it's equal to 0, we get n plus a. Okay, well, I'll turn it into a definite integral, seeing we've got an initial value problem there. So it will become the integral of the y over y minus n is equal to some constant times the integral of the x. We know when x is 0, y is n plus a, and we want to link x and y together. So on the left-hand side, we get a log function. Right-hand side is just constant times x. So subbing in our values, we get the log of y minus n over a. Okay. Well, I'll exponentialise both sides, get rid of that log. So e to the power of x is the absolute value of y minus n over a, multiplying by the a. Now you'll notice I got rid of the absolute value signs here. Why did I do that? Well, because a could be plus or minus itself. And look what we end up with. Y equals n plus ae to the kx, which of course was our modified growth and decay equation from last year. Let's have a look at this one. Y dx is e to the power of 2y minus 1. Well, that becomes e to the power of 1 minus 2y. Over on the left-hand side, integrate both sides. Let's play around with this one. We want to make y the subject. So what do? Well, multiply by the negative 2. Then this time I want to get rid of the exponential, so I'll log both sides. And playing around with it, eventually, there it is. Y equals a half. 1 minus the log, but this time our constant's inside the log itself, so constant minus 2x. Square root of 1 minus y squared. So integral dy on the square root of 1 minus y squared is integral of dx. That's an inverse sine function, so we end up with y equals the sine of x plus a constant. We're going to look at a specific differential equation here known as the logistic equation. Now, the standard one looks like this. So the derivative of some function of x will equal that function of x times 1 minus that function of x. Our syllabus says we're going to restrict it down to simply where we have something like this, where function x is simply y. So it becomes the y dx is equal to, we could have some constant, so constant times y, and instead of 1 minus, you could have another number, so p minus y, but it's still of that sort of form. But as I say, in this one, function x is y. So let's look at this then. Y dx is, let's make it easy, we'll make that p equal to 1, we'll make that constant equal to 1 as well. So we'll get y, 1 minus y, we'll make it an initial value there of when x is 0, y will be a, some constant value. The slope field for that, there it is. Now, there's 3 different curves you could have. 3 different curves, because there ends up being horizontal lines. Now, the axis is one of them. Whilst it's not actually drawn in there, but I hope you can appreciate, look, down here it's going down, here it's going up, so somewhere in between it must have gone horizontal. So depending on the values of A, which one of those 3 we could get, but also we could end up with the 2 trivial solutions as well, where the actual, what we're looking at as asymptotes, is a solution in itself. Have a look at the original equation. Again, we could have picked up those trivial ones, because if we were to separate the variables on this, we would have divided by the y, 1 minus y. So possible for y to equal 0, y equals 1 in that case as well. So they'd be our two trivial solutions. So in fact, there's actually 5 possible different solutions. There's a word there that's not necessary, isn't there? All right, here, let's work it out. dy dx is y, 1 minus y. We'll divide by the y, 1 minus y, separate our variables. They gave us the initial condition. When x equals 0, y was equal to a. We want to link x and y together. So the right-hand side, well, it's just going from 0 to x, so that just becomes x. Left-hand side, I've done a bit of partial fractions there, but it's quite an easy one to do. I get 1 on y plus 1 on 1 minus y. So they are both log functions. Maybe I've done too many steps in one there, but if you look at it, the first one's going to become log y. The second one will become minus log 1 minus y. Used my log laws, combined them into 1, so I've got y over 1 minus y. Substituting in the y and then the a, again I've done it all in one step, because I know when I substitute the y in, that will be on top. When I substitute the a in, again I'd be going minus the log, combine them together, we'd end up with that. So x is equal to that. All right, I want to get y the subject, so get rid of the log. E to the power of x is equal to the absolute value of that. So I'm saying ae to the power of x is equal to y on 1 minus y, and I've defined the absolute value of a to be a on 1 minus a. Because at the end of the day, that's going to be a constant number. So ae to the power of x, 1 minus y equals y, play around with it. I come up with that one, and I suppose that is an answer, but we tend to see it in a different form, and it really is the same thing. I've defined b to be the reciprocal of a, but the other thing I've done is I've basically divided everything by e to the power of x as well, and we end up with be to the minus x plus 1 on the bottom. So there are my 3 solutions. I've got the 2 trivial solutions, 0 and 1, and then I've got the other solution, 1 on be to the minus x plus 1. And you might be thinking, hang on, you said there was 5. I've only got 3. Well, that's because that third one there actually contains 3 different solutions. Depending on what the value of a was, you get the different ones. Find any inflection points in the logistic curve. All right, well, what do we know? We know they're going to possibly happen when the second derivative is equal to 0. Well, the second derivative is the derivative of the first derivative. The first derivative was the original equation that we were given, y 1 minus y. So I'm just differentiating that to find the second derivative. Oh, hang on, with respect to x, I got to use implicit differentiation now. So I can differentiate that with respect to y, and then I'll multiply that by dy dx. So, follow me here. The first bit, I've differentiated with respect to y. Write down the first, diff the second, plus write down the second, diff the first. Or I suppose I could have just expanded it out and did it that way, I mean, either way. But times dy dx, but we said dy dx was y 1 minus y. So I'll get that in there. And there it is, y times 1 minus 2y times 1 minus y. We want to solve when is that equal to 0. So I have 3 possibilities, but they're not all inflection points. Only one of them is. The only one that's possible is a half. Because remember, y equals 0 and y equals 1 were our 2 trivial solutions. We know those to be straight lines. Well, there's no inflection point on the straight line. The other one, and if you look at the slope field, you'll see it, that yes, that will change concavity around about where y is equal to a half. Okay. Now, we haven't found the inflection point yet. We've only found the y value. We now have to find the x value. So be to the minus x will equal 1. Now that goes back to our equation there when I've set that equal to a half and played around with it to make, let's go back, here we go, to make be to the negative x the subject. So I've got it to that point. It's equal to 1. So e to the power of x is equal to b. X is the log of b, but remember, we defined b to be the reciprocal of a, and we defined capital A to be, what was it, a over 1, or the absolute value of a over 1 minus a. So I now know x is equal to the log of 1 minus a over a. We should mention about the change in concavity here. I'm not going to bother finding the third derivative, and I'm also not going to bother testing either side. I'm going to simply say, well, look at the slope field. You can see from the slope field that there is a change in concavity. So there's our point. The x value is the log of the absolute value of 1 minus a over a, and a half is the y value. 13D.